Hi, welcome to CS70 Video Solutions for Homework 3. I'm Dixon Tsai, one of the readers for this course, and video solutions are meant to be a brief but comprehensive supplement to the regular written homework solutions, where I'll be going over my own approaches to these problems, highlighting some alternative solutions, and pointing out some subtleties in the concepts that will help you understand the material a bit better. If you have any feedback on the video solutions, please search video solutions on Piazza, and I'll try my best to tune my solutions to your needs. Let's get started. Welcome to problem 1. You'll see that this problem is very similar to the dragons problem you got on your previous homework. And so, what's different about this problem? Well, and what clues can we glean from the description? Well, as you see here, we need to prove that all battles end with the ninja fleeing. And when does the ninja flee? When there's only one ninja left. And you'll see that you're given this very handy formula, so you actually don't need to read the description. When you're taking a test, you want to hone in on what we are specifically asking for you so that you can spend more of your time thinking about the math rather than being stuck on the story. Excellent. So we now discovered these clues. What do these clues tell us? N is greater than or equal to 1 because you have one or more ninjas, and N is discrete, so which basically means that you can't have fractional ninjas. Excellent. So these two clues together give you a strong indication of induction, which you'll need to prove whatever you want to prove. Now, how do we formalize the statement? Well, you can see that for any given n that you start with, you have to repeatedly apply this function. So after a certain number of applications, you'll eventually reach 1. So, given this pattern, we need to write a statement. So, prove that for all n, after repeated applications of f, this whole expression will go to 1. So this is what we need to prove. We know that we need induction. Now let's take a closer look at what the proof structure should look like. So we know that we need a proof by cases. Why? Because you can see that we have a piecewise, we have a conditional function here where you have 3 different conditions. And then, how many base cases do we need? Well, since all the numbers end up going to one landing spot, 1, so one landing spot, we only need one base case. And finally, for induction, can we just have simple, or do we need to use strong induction? Well, it's hard to say where we'll end up after applying this function. So we'll need to guarantee that all the numbers between the base case and where we end up with, so say we're proving n, we're gonna go somewhere here and then end up who knows where. So that's why we need to use strong induction. Excellent. So we pretty much outlined the technique we're going to use. Now we just have to execute. So let's start with the base case. And this is simple enough. We just say let n equal 1. Since we're already at 1, right, then we're done. So the proposition of n is true. Excellent. So inductive hypothesis. Assume that for all k between 1 and n, p of k is true. This is important. And now the inductive step. We want to prove that f of k plus 1 goes to 1. So how do we do this? Remember, we have 3 cases when we first apply f to n. So 3 cases. And I'll give you a moment to write everything down before I continue. Now, the 3 cases. Case 1, right, is when n is divisible by 4. So if k plus 1 is divisible by 4, then we get this expression. So f of k plus 1 equals this, which equals k over 4 plus 1 over 4, which is clearly less than k plus 1, the original value we start with. And this is important because since smaller, invoke the inductive hypothesis. And since we assume this is true, the inductive hypothesis is true, then this k plus 1 is true for case 1. Now case 2, f of k plus 1 will be equal to k plus 1 plus 2 over 4, which is k over 4 plus 3 over 4, again, clearly less than k plus 1. So now we invoke the inductive hypothesis and give it a green light. Now case 3 is a more interesting case because when you first apply f of k plus 1, you'll get 3 of k plus 1 minus 1. So this actually increases. But what do you know about 3 and odd numbers? Remember, this is if k plus 1 odd. So when you're stuck, let's create a lemma. So clearly, if you have this whole thing turn into another odd number, then this ninja problem is contradictory. But here, we can prove that 3 of any number m minus 1 will, with m odd, will always be even. And how do you prove this? Well, if m is odd, then m is equal to 2k plus 1 for some k in the integers. And now, 3 of 2k plus 1 minus 1 equals to 6k plus 3 minus 1 equals to 6k plus 2. And this is equal to 2. So this is clearly divisible by 2 since we have the factor of 2, and so this lemma is true. Alright, so now that we've proved the lemma, we can use this to say f of k plus 1 will be even. So we can use this worst case when n is even but not divisible by 4. This will give us 3k plus 1 minus 1 plus 2 over 4. This is 3k, pardon my writing, plus 4 over 4 equals to 3k over 4 plus 1, which is clearly less than k plus 1 because 3/4 of k is less than k. So now we can just invoke the inductive hypothesis and place a check mark. And now we've proven that for the k plus 1 case, when we take the inductive step, we will always get a result that is smaller, and that smaller result will go to 1 based on the inductive hypothesis. And therefore, we have proven that all battles end with the ninja flame.